Majority element. Have you ever stared at an array and wondered which value silently dominates the room? Majority element is a Pattern Mastery 100 essential and a favorite warm-up at Fong screens. Mastering it proves you can turn raw iteration into sharp insight with O1 space. Today we'll crush it using the basic framework and the legendary Boyer-Moore voting trick. Fast, elegant, unforgettable. Breakdown. We're given an integer array and guaranteed there's a majority element, a value that appears more than n/2 times. Our task: return that element. Because a strict majority exists, it must be the final winner if we pair off different elements until one remains. Assess. A hash map count would work in ON time but ON space. We can do better. Boyer-Moore voting runs in ON time and O1 space by tracking a running candidate and a count. When we see the same value, we vote +1. A different value votes -1. Whenever the count drops to 0, we switch candidates. With a guaranteed majority, the final candidate is the answer. Structure. Plan. Initialize candidate equals none, count equals 0. Iterate through the array. If count equals 0, set candidate to the current number. If current equals candidate, increment count, otherwise decrement. At the end, return candidate. If the problem didn't guarantee a majority, we'd re-verify by counting, but here it's guaranteed. Let's try to implement it using solution 1. Time complexity is ON. Space complexity is ON. This solution uses a hash map to count frequencies. The majority element is the number that appears more than half the time. So we calculate a threshold. The threshold is floor of n divided by 2. Then we scan through the array once. We update a running count for each number in the map. The moment any number's count crosses the threshold, we can return it immediately. At that point it is guaranteed to be the majority. First, we create a map to store how many times we have seen each number. We also compute the threshold. That is more than half the array length. Any number that crosses this value is automatically the majority. Now we loop through the array once. For each number, we grab its current count from the map. If it has not appeared yet, we treat its count as 0. Then we add 1, and we store it back in the map. This keeps a live frequency table as we scan. Right after updating the count, we check if it is greater than the threshold. If it is, we return that number immediately. There is no need to keep scanning. It has already appeared more than half the time. And that's how this algorithm works. It first sets up a hash map and a majority threshold, then it counts occurrences in one pass and returns immediately when a number exceeds half the array size. Efficient, simple, and elegant. Test case check. Majority element, hash map counting. Let's test our function using this input. 3, 2, 3. This array represents a list of numbers, and our goal is to find the majority element, the value that appears more than half the time. Here's why the solution works. We build a running count for each number using a hash map. As soon as any number's count becomes greater than n/2, we return it immediately, because by definition, that number must be the majority. And that's exactly what our program outputs. 3. It matches the expected majority element perfectly. Wrap up. So, our implementation is correct. The algorithm successfully identifies the element that appears more than half the time. Simple, efficient, and accurate. Let's try to implement it using solution 2. Time complexity is ON. Space complexity is O1. This solution uses the Boyer-Moore voting algorithm. It is a clever way to find the majority element without extra memory. The idea is to cancel out different numbers against each other. We keep a candidate and a count. When we see the same number as the candidate, we increase the count. When we see a different number, we decrease the count. This is like pairing them off and eliminating one vote. If the count ever drops to 0, it means the current candidate has been fully cancelled out so far. So we pick a new candidate. Because a true majority element appears more than half the time, it cannot be fully cancelled out by all the other numbers. So it survives as the final candidate. We start with 2 variables. Candidate holds the current best guess for the majority element. Count tracks how strongly the current candidate is winning compared to other values we have seen. As we scan through the array, whenever count hits 0, we reset our candidate to the current number. That is like saying up to this point everything is balanced out. So we start fresh with this new value as the candidate. Now we do the voting. If the current number matches the candidate, we increase the count. If it does not match, we decrease the count. This is the canceling effect. Different numbers reduce the candidate's advantage, but the true majority will still come out ahead overall. After one full pass, the remaining candidate is the majority element. It is the value that could not be cancelled out by all the others. And that's how this algorithm works. It first sets up a candidate and a vote counter, then it scans through the array cancelling out different values until the true majority survives as the final candidate. Efficient, simple, and elegant. Test case check. Majority element, Boyer-Moore voting algorithm. Let's test our function using this input. 2, 2, 1, 1, 1, 2, 2. These numbers represent a list where one value appears more than half the time. Our job is to identify that majority element. Here's why the Boyer-Moore algorithm works. We keep a running candidate and a count. When the count drops to 0, we switch the candidate to the current number. Then, for each element, we add to the count if it matches the candidate or subtract if it doesn't. And that's exactly what our program outputs, too. It matches the expected value perfectly, proving the voting algorithm worked as intended. Wrap up. So, our implementation is correct. The algorithm successfully narrows down the majority element using constant space and a single pass, efficient, accurate, and reliable. Majority element. Let's do a recap. Ever face a problem where one number seems to quietly take over the whole array? Majority element is that test of insight, a simple setup that exposes whether you can think beyond counting and find patterns in balance and dominance. Breakdown recap. Conceptually, we're finding the element that appears more than half the time in an array. Because that majority always outnumbers the rest, even if we cancel out every pair of different elements, the true majority will still remain in the end. Assess recap. We compared two main approaches, using a hash map for frequency counting versus the Boyer-Moore voting algorithm. Both run in ON time, but Boyer-Moore uses just O1 space, elegant, efficient, and the clear interview favorite. It tracks a candidate and a count, adjusting as elements vote for or against it. Structure recap. We structured it around one simple rule. When the count hits 0, pick a new candidate. If the current number matches it, increase the count, otherwise, decrease it. By the end, the guaranteed majority remains as the final candidate, no second pass needed. Implement recap. We ran the logic step by step in LeetCode, and it executed perfectly. No errors, no extra space, just clean, consistent majority detection. Check recap. All test cases passed. The algorithm correctly identified the majority element across different arrays, confirming that our approach worked exactly as expected. Closing insight. The takeaway? Majority element teaches one of the most elegant uses of mathematical balance in algorithms. Once you understand how to cancel out competing values, you'll start spotting similar patterns in many optimization and voting problems. Fast, clean, and interview-proven.